Welcome, everyone, to the very first episode of the Hard Tech Podcast. The purpose of this podcast is to showcase the big ideas that are going to potentially change the world and feature some of the scientists, engineers, entrepreneurs, and investors that are leading that charge. Today, on the very first episode, we have the one and the only Martin Tajmar of the University of Space Physics in Germany. We will let me read his intro here. Professor Tajmar, is it Tajmar or Tamar?
It's Tajmar.
Tajmar. I assume that you probably get that a lot, right?
Yes. From English-speaking folks, yes, that's right. Yeah.
Okay. So Professor Tajmar obtained his BS and MS in physics and a PhD in electrical engineering from the Vienna University of Technology in Austria, as well as a master's in space studies from the International Space University in Strasbourg, France. In 1999, he joined the European Space Agency as a young candidate trainee in the electrical propulsion section, and in 2000, he moved to the Austrian Institute of Technology, where he was appointed head of the Space Propulsion and Advanced Concepts Department in 2005. From 2010 to 2012, he was an associate professor for aerospace engineering at KAIST in Korea. In 2012, he was appointed full professor and head of the Space Systems chair at Dresden University of Technology in Germany. He's developing electric and advanced propulsion, space transportation, and microsatellite solutions. And since 2014, he's been the director of aerospace engineering at the Institute of Dresden. It's safe to say that if we're talking about space propulsion, Dr. Tajmar, you would be qualified to do so. So welcome to the show. It is a pleasure to have you. Really thank you so much for taking the time today. Wanted to get right into it. Why don't you talk a little bit about your background as far as like what interests you in physics, and why did you decide to become a physicist?
Well, I always knew that I would like to become a physicist. I'm very curious about nature, how things work. I'm especially interested in everything that deals with gravity and propulsion. So that's how I ended up. Really, when I was 5, 6 years old and people asked me what I would like to become, I said I would like to become a physicist. People were really amazed because at this age, how does someone know? They asked me if I even know how to spell it, correctly, physics. Yes. But yeah, I said I would like to become a physicist. And when I watched Star Trek, and I saw, how to travel to other stars, and there's the warp drive, I said, well, someone is going to do it, so I have to work on the warp drive, and someone has to do it. So that's how I got into the game early on. Yeah.
You mentioned gravity and those types of advanced propulsion. As far as physics go, I don't think there are any other scientists that are interested in that kind of field. It seems like a really interesting idea. Could you elaborate on that a little bit?
Why gravity? Well, gravity is gravity and everything around gravity is kind of our limiting factor in current space propulsion, right? So you wanna go into orbit, you have a huge rocket, and you spend an enormous amount of propellant just to bring a little tiny thing up there. Why? Because you have to escape the gravitational field and this kind of stuff. So if you would launch from the moon, things are so much more easy, right? So gravity is the kind of a thing that limits our propulsion capabilities, because we have to launch from Earth. So that's kind of a starting point. That's the hard thing. It's hard because of gravity. Yeah? At least within the solar system. If you want to go past the solar system or so, then the other things that are very hard. But let's say within our solar system, gravity is the #1 issue.
Gravity is the #1 issue.
Yeah, I mean, we so far it's an engineering problem, right? So we know it's hard, but with enough money and with enough expertise, we can do it. It was hilariously expensive. Elon Musk is changing this a little bit, that it becomes much more affordable, because instead of riding an airplane once and then trash it. Now we will go for reusable rockets.
Yeah.
And well, the big difference is we already had a reusable rocket. It was the space shuttle, but the space shuttle was more expensive than anything else. So the big difference is that Elon Musk is making reusable rockets, which are cheaper than everything else. So that's the big thing. And if it becomes more affordable, then okay, well, you have to spend a lot of propellant, but okay, well, propellant cost is not that expensive. Yeah, if you can reuse the rocket, and yeah, you just have to fly a couple of times up there, refuel your spaceship, and then off you go to Mars. So that's plan A right now. So we can explore the solar system, despite the fact that it's hard to overcome the gravitational field from the Earth. It's an engineering and money exercise. Yeah.
You said gravity is I just want to focus on, you said gravity is an engineering problem.
For us, I mean, if you wanna leave the Earth's gravitational pull, then it's an engineering exercise. We can do it, right? It's expensive, but we can do it. And with some little more engineering, we can make it more affordable. Yeah. So it's not a showstopper, right? If you want to go to the next star, there are a couple of showstoppers. This is not necessarily an engineering exercise, but it's kind of a science challenge. But for the solar system, so as a first step, it's an engineering exercise. Of course, if you invent something much better, right? If you come up with a much more clever idea, then it will become even much more affordable. But the way Elon Musk keeps going, it will become pretty affordable. So at least something.
So we're talking about conventional rocket propulsion, where the rocket itself has to take up the amount of fuel, and also has to probably take into account the weight of the fuel that is bringing to fly the fuel up into the air. That's the current method that we use to transport material into space, right?
Right.
So what are the other options? It doesn't seem like there are any currently, right? Or are you talking about electric propulsion, nuclear propulsion?
Sure. I mean, those are, if you go for, let's say, electric propulsion, so that's usually in-space propulsion. So once you're in space, well, depending on where you want to go, then you still need significant propulsion. Just if you launch a satellite and you want to keep it there, well, you have to do propulsion basically all the time for attitude and orbit control. So for, let's say, for a typical satellite in geo orbit, so telecom satellites, half of the propellant is half of the spacecraft is propellant. So yeah, it's actually quite a lot. So you can improve on that by saying that instead of chemical rockets, I don't need such high thrusts anymore. I would rather like to focus on efficiency. Then, for example, I would go for electric propulsion. That's now the mainstream in-space propulsion option because it's much more efficient. The thing is, when you have a rocket, chemical rocket, then well, you create a hot gas, and this gas is coming out one way, so you're accelerating the other way. And the thrust that you produce depends on the mass flow rate, so on the amount of propellant that you consume, and the exhaust velocity. And this velocity is limited by the temperature of your gas. And I'm limited by the temperature of my gas with the materials that I'm using, right? So I don't want to melt the engine, so I'm limited here, right? So for chemical propulsion, there is a certain limit, and this limit is actually not, well, it's not very high. And the efficiency is actually pretty low. You can do much better by, for example, saying, I don't care about temperature. I'm accelerating my propellant with electric or magnetic means. Then speeds become much higher. I need much less propellant to do the same job. On the other hand, if you know, the chemical engines, they had all the energy in their propellant. So now I have to bring in external power. My spacecraft now has to power my engine. And if I have solar arrays, you know, I have some kilowatts available. Comparing this to, for example, a rocket engine, you know, a big rocket engine has a power density of a gigawatt per cubic meter. And well, that's a lot. That's a nuclear power plant, you know, the size of a human being. So that means if I now have much less power, that means that my thrust will go down. So I have less thrust, but much more efficient, which means my maneuver now takes much longer time. If I have the time, or if I don't need high thrusts, no problem. Yeah. So if I can afford to, you know, coast for a couple of years to my next target, no problem. I go for electric propulsion. If I want to go there quickly, then maybe I need this booster, you know, chemical propulsion stuff. So I have different options. But let's say for day-to-day operations on a satellite, I'm going for electric propulsion. The kind of in-between, better efficiency and still super high thrust, that would be nuclear propulsion, as you said. Yeah. So with nuclear propulsion, then I can heat up everything just with nuclear power, and everything means that I can heat up also the lightest element, the lightest propellant that is around, which is hydrogen. And that means that my exhaust velocity is much higher than if I would have to combust hydrogen, for example, with oxygen. Water is much more heavy than just pure hydrogen. So if I can go with pure hydrogen, that's great. And I get the same power density compared to chemical propulsion because of a nuclear reactor. So that would be the next evolution. And well, the Chinese have this on the drawing board. The US had it on the drawing board in the 60s and 70s, and I'm sure before the Chinese are going to do it, the US will try to do it as well. And well, Russia has it on the drawing boards and whatever. So that
sounds exciting.
Yeah, in the next decade, for sure, this is a tech that is going to be unleashed. And in space, that makes sense because you want to talk about, you know, radiation in space. Space is full of radiation. So this is very different, right? If you are here on Earth, then a nuclear power plant is maybe not such a good option because, you know, what to do with all the waste, and there are plenty of other options, you know.
A fission plant. A fission plant.
Fission plant. Yeah. So I go with solar, right? My roof has a nice solar roof. So I go solar. Yeah. In space, actually, the whole space is full of radiation, you know, from the sun. So there, actually, it counts. The quicker I go. So if I go to Mars, let's say 2 months, and even if I would have a nuclear reactor with me, the radiation dose that my astronauts are exposed to is actually less than if I would go with chemical, and it takes, you know, 6 to 8 months to go to Mars. Because in space it's full of radiation. Yeah?
So getting there faster is you're exposed to less radiation than if you were to take longer using a conventional rocket.
Even taking into account that I have a nuclear reactor on my back, right? So that's a nice thought. So that will come. This technology is going to come. Of course, this is also more for in-space propulsion because we don't want to launch with a nuclear reactor, you know, active, fully operational here from Earth. If something happens and so on. So this is an in-space propulsion option as well. There are, of course, other concepts how you can go into space than taking all the propellant with you. For example, you can use air breathing propulsion, right? Why taking all the propellant with you if you launch through the atmosphere, and the atmosphere is full of potential fuel, right? You could take oxygen from the air. That would drastically reduce your propellant mass on your rocket, and yeah, this would become much more affordable. Well, of course, there are lots of problems associated with this technology. That's why we have not realized it yet. Another potential technology is to ride on top of a laser beam, for instance. Yeah, so you have the power source on Earth, and you push with a laser beam. Maybe you can launch some small spacecraft with that. People thought about launching from a catapult and whatever. There are a couple of interesting alternative concepts to the usual rockets.
Seems like it's going right back to, you know, the cartoons.
Sure,
Slingshot.
Why not? None of them people seriously try to do that. Yeah. So. I mean, I think in the US, there was a gun developed in the 1960s that when I fired the projectile reached an altitude of 180 kilometers.
That's like low Earth orbit almost.
Well, not almost, because space starts at 100 kilometers.
Oh, so
So
there, oh yeah. So
yeah,
yeah,
yeah.
you're in space.
And you can't shoot at something with
Yeah,
a big gun. So it's possible.
yeah. You can't put a person in there, but probably a drone.
Yeah,
Yeah.
but yeah, some special payload maybe.
Hmm.
Yeah. So there are a couple of alternative concepts, let's put it like that.
Yeah.
In addition to rockets. Yeah.
It seems like, at least in the US, in the early 1960s, there was a big push for like really big ideas, right? It was nuclear powered everything. They wanted, we talked about nuclear powered cars. There was this one car, I remember it was called the Nucleon. It was
Mm,
supposed to get about 1,000 miles, per refuel, and there was a nuclear powered engine in the back.
mm.
And so obviously the car did not go into full scale production, but it was a concept of the just big ideas. People were really interested in big ideas, and they paid attention to big ideas, and they pursued them. Why do you think that some people are drawn to really big ideas, and other people not so much, at least because it seems like from some of the research that you're doing, they're all really highly impactful potential ideas. Alternate propulsion, space travel. You talk about in the solar system and outside of the solar system, whereas other people are not really looking that far long range. So what do you think is the difference there in the mindset?
Well, first of all, I think this is my responsibility as a university professor. I'm not industry, so industry is already building rockets, building satellites, and Elon Musk is maybe going to Mars. As a university, I have to think far ahead, right? I have to develop the next concept, yeah, and think about those things to push the limits that will then eventually lead to new industries and so on. That's my role for university. I have to really think far. Especially, you have to set a goal which is really very much up there in order to achieve something.
Mm-hmm.
If you want to achieve just a little thing, then well, it's just an engineering and money exercise.
Mm-hmm.
This is well, next year we have achieved it, and then what? So I rather like to set an impossible goal, and well, if I'm lucky, of course, I will maybe achieve it, or maybe halfway or whatever. But if I set a really impossible goal, I'm absolutely driven by innovation. I have to be extremely innovative, and maybe I will discover something that I've not expected at all. Maybe something could be different. But I need to make a very hard to achieve goal to achieve a big step forward. That's very essential.
That's the quintessential definition of hard tech, right?
Mm.
You're talking about a goal with a tremendous upside, extremely challenging, extremely expensive, relatively low likelihood of success, and yet, there it due to the impact and due to the potential implications, we pursue it, right? And I think that's a very admirable, and I think that's a phenomenal thing to be doing, because really and truly, the next generation of technology that we're going to have that are going to change the world are going to be coming from the hard tech space. There are people that are developing nuclear fusion, people that are talking about carbon capture, like yourself, alternate forms of propulsion, potentially gravity propulsion, or even electric or nuclear, for that matter. So I think it's extremely important, as you said, to set a big goal. And even if it is potentially impossible, the learnings that you're going to get on the back end, they're going to more than pay for it. Because you're
Sure.
going to be driven by innovation, right? In the Manhattan Project, I think, when we developed the very first nuclear bomb, this was a completely new endeavor. I think there was something about 1,000 patents, for unrelated different pieces of technology that were developed as a result of that one goal. So in the same way, I can see the same thing happening here, and from the propulsion space. I read this. I read a quote, from Jeff Bezos from Blue Origin, and he talked about space travel. And he said there are two problems with space, right? It's both extremely dangerous and extremely expensive. But aside from that, it's fine, right? You know, you know, are there any what do you see, as like, some of the challenges? You mentioned that gravity is one of the biggest challenges for going into the solar system, but then there are other challenges if we're trying to go even further into like interstellar space. What could you speak a little bit about some of those challenges?
About going interstellar? Well, I'm always using this kind of comparison. Let's imagine we want to go just to the next star. Okay, so this is 4 point something light years away. This is the next star. Maybe there is an interesting exoplanet we have identified, maybe an interesting planet, but not sure if there's life or whatever. We just know there may be an interesting planet there. So let's go to just our next neighbor, right? And let's go there without coming back. Yeah, let's just go there and let's try to be lucky. Yeah. Next thing is let's try to go there within 40 years. That well, if we start in our 20s or whatever, that we make sure that we are still alive, to get there or whatever. Okay, so 40 years, still being alive, just to the next star, not coming back, and then maybe we would like to have a spaceship at least the size of the space shuttle. Yeah. So right now, SpaceX Starship is about twice the space shuttle. So yeah, it's not that big, but well, just for me alone, I just need a couple of books, and I maybe need some food. So I checked for these 40 years, maybe half of the cargo bay from the space shuttle is enough for all this canned food that I have to take with me to survive for 40 years. I can choose between tortellini and spaghetti or corned beef, for 40 years.
A lot of corned beef, yeah.
Sounds fun, yeah. And okay, maybe I need some oxygen or whatever. So the space shuttle for 40 years, yeah, and yeah, I have to try to not to get too much bored. Now, what kind of propulsion system do I need to make sure that my space shuttle will arrive in 40 years to the next star? Let's take the best option there is. We already mentioned nuclear propulsion. Well, there is a nuclear propulsion option that tops everything, okay? And you mentioned Manhattan Project, that's it. So I just take a nuclear bomb, a small nuclear bomb, I drop it behind the space shuttle and I push the ignition button. That's the biggest blast that we know that we can make, right? And we are riding on this shock wave, and well, that's the biggest push we can imagine. You will think that's crazy. In fact, people were working on this and trying to develop this. There is a test
Really?
around for that idea, okay? It's called Project Orion. Yeah, in the 60s, everything was possible, as you said. So that's the best nuclear propulsion system we can think of. Just ignite the nuclear bomb, right? Now, how many bombs do you need to get the space shuttle to the next star? And if we crunch some numbers, the mass of the nuclear bombs that you have to take with you on a trip is the mass of the sun.
Whoa.
Okay, so that tells you how impossible it is. Okay, this is not something, well, maybe with a little engineering or so we can make it work. No, that pretty much means it's not going to happen. Not with nuclear bombs and not with whatever we thought about propulsion up to now. No way. Maybe we can send something the size of a computer chip to the next star, maybe to just do some nice photos or so. That's a project called Breakthrough Starshot that people are working on. So you need something like a 100 gigawatt laser on the Earth. That's the power of 100 nuclear power plants connected together.
The biggest laser we've ever built.
Yeah, well, not only that, but how do you get this amount of power channeled into something? So the power challenges really a lot, and then you fire on a spacecraft the size of a microchip. Now, some people will say, okay, this microchip is gone. it's gone for good, because if I fire this amount of power on a computer chip, it ceases to exist, right? It's just gone, okay? But if you have a super mirror in front of it, okay, that somehow reflects this photons from the laser, just that you develop, an incredible push, and you pinpoint exactly to the next star, then you can accelerate to something like 20% the speed of light. Then in 40 years, your microchip will arrive at Alpha Centauri and will make a few pictures. Of course, the next issue is how shall it transmit these pictures back to Earth, this little microchip? Where's the energy coming from? How does it survive for 40 years and whatever? And for me, I think the biggest issue is you fire with this laser beam towards the next star. If you make a mistake by, I don't know how many fractions of a degree, this probe will arrive anywhere but at this next star. So yeah, lots of problems, but theoretically, if you calculate it through, it's possible. If you are really lucky, you get the right angle, you have the high reflectivity and whatever, you can make this work. Maybe for a microchip. Well, so I would say the best option right now is to work on space telescopes to make them better and better, and to check, if we can get a nice picture of this planet and check if there's anything worthwhile. That's maybe the best thing, because with technology good to go there, it's just so impossible. So there's always a plan B, right? I'm always, as a good engineer and a physicist, you always have to think about a plan B. Maybe if it's so impossible, yeah, and then maybe the biggest problem is just us, okay? We have a problem with these 40 years, because if it lasts longer than 40 years, then we have a problem. Not necessarily that technology will have a problem with this, right? But it's just us. We have a problem with this, okay? So that means maybe that, it was our duty in history to come up with artificial intelligence. And we send an AI robotic probe to the next star. Maybe it takes 10,000 years or so for this AI. Not a problem. Maybe this AI is also not going to be bored, just waiting patiently to arrive there and then making pretty pictures and trying to establish some communication back to Earth. Maybe that was our role in the whole evolutionary path, set for us. But maybe this was just this piece in the puzzle, of how to conquer and expand in the universe. It's just not going to be us humans in a biological sense. We just live too short. So that's at least that is something that we can do. That's the least thing that we can do. Send off something that takes a long time. We just have to make sure that it still works afterwards. So yeah.
We'd have to stay in our. It seems like we're going to be in our own solar system for the foreseeable future. But we'd probably be able to take some pictures and get them back in 10,000 years.
Yes. So that's something that something that you can outline, unless of course something comes up with an idea how to travel. Yeah.
The warp drive.
Yeah, with a very different concept, like the warp drive, like in Star Trek, to go there, but it's obviously based on something entirely different. Yeah. Just something that we don't know how to do yet.
I see. I remember reading something where they talked about, the warp drive would essentially, like a working warp drive would be dependent on almost like negative mass in order for it to work. Is that accurate, or is there some accuracy to that based on?
Well, you can. I mean, if you bring me -1 kilogram, I can assemble your spacecraft going to the next star immediately. That's the catch. The thing is, theoretically, this is just a theoretical idea. We can work out the math, saying that if I would have negative mass, I know how to do the trick. So at least theoretically, we know, hey, there's a trick. It's maybe not the only trick, maybe there are others, yeah, but this is one trick we know of. Problem is, where is negative mass? Antimatter. Well, that's maybe one option. The thing is, well, this is under investigation. So there are several experiments running at CERN, for instance, this biggest particle accelerator in the world in Switzerland. And they already announced some preliminary results. We already know from a couple of other experiments that that antimatter almost 100% sure is not negative mass, unfortunately. But well, there's still some. They're trying to. They want to, for example, check how anti-hydrogen is falling down, because the problem is, for example, it's really hard. Antimatter, it's this mirror world, right? So not everyone knows that. So if you look in a mirror, this is how it looks back. So for example, the electron, if an electron has a negative charge, it looks in the mirror and it sees everything reversed. So it sees, oh, instead of minus, I'm plus. Okay, so you can make positrons pretty easily, but it's very hard to check how a positron is falling in a gravitational field, because it's electrically charged. Everything that is electrically charged, electromagnetism, is so much more stronger, so many orders of magnitude stronger, that it's very hard to make an experiment to check how it's falling down, because it's so much more influenced by electromagnetic fields. So you need, preferably, you need an antimatter atom. So something that consists of positive and negative charge, for example, anti-hydrogen or anti-helium. That would be fantastic, because it's not charged, so it has no net charge. It's electrically neutral, and I can just check if it's falling down or falling up or whatever. So that's what they're trying to do at CERN, and they will have a result on that pretty soon. And well, if it falls up,
there's a negative mass.
I'm not sure. But there are lots of consequences for that if it would fall up, yeah. Because, for example, yeah, it's really hard, yeah. If you say you have negative mass, then yeah, you would fall up in a gravitational field. On the other hand, if a force is acting on you, okay, it's not only gravitational mass, but also inertial mass. If you have negative mass and you're trying to push it, it's coming actually to you. It's not, it's exactly the reverse thing.
Yeah.
That means if an antimatter, yeah, if anti-neutral matter has a negative mass, it would still fall down in the gravitational field, because gravity is repelling it. But when it's repelling it, it's actually accelerating still downwards. So it's really hard. It's really hard. Yeah.
So, but it would do the opposite of helium, right? Of hydrogen, right? So an antimatter atom of hydrogen, wouldn't it theoretically do the opposite of the standard matter? Oh.
What I just said is, if you have helium or hydrogen and let it fall, it falls down, right? And what I just said, if it would have negative mass, and negative mass meaning both negative gravitational mass and negative inertial mass, it would still fall down. So you cannot distinguish by letting it fall down if it does the same. It would fall up if it would have, for example, a positive inertial mass but a negative gravitational mass. Then it would fall up. But that would go against equivalence principles. It's really hard. You have to do some really lots of different experiments to find out what's really going on. Yeah. So for example, you would have to go in a centrifuge, and you would have to see if this anti-helium is also going out or if it's going in. Then I would know, hey, this stuff behaves strange. But simply letting it fall, it may fall the same way as normal matter is falling, so you wouldn't know. Yeah? It's really hard unless the equivalence principle is broken. So there are many things you have to take into account. But yeah, maybe antimatter, but chances are, well, you have to do the experiment, of course. That's number one thing. But there are a couple of experiments already out there that tell us that it's probably not going to be the case.
I see. Now, as far as like your research goes, in terms of like for the audience, could you explain in like the simplest terms, like what's some of the research that you've been doing?
Okay, the research that I'm doing, let's say in that area, because I'm doing lots of things. Yeah, so we just launched our third CubeSat satellite. We are We are building sounding rockets with new type of engines and whatever. So now let's talk about breakthrough propulsion. So this is my passion since I was a child watching Star Trek. What I'm trying to do there is the following. First of all, of course, I'm trying to check, you know, who did what. Are there some interesting experiments out there that are interesting for an evaluation? Are there interesting theories out there, like we just said, what happens with negative mass that would lead to maybe something like a warp drive? So that's the one thing, to do a survey of what's really out there. The second thing is to build testing infrastructure that allows you to really safely assess such concepts and to look beyond, or to look into areas that no one has looked up to now. Yeah, because that's essential to find something new. Because the bad news is that everything up to now that is out there and everything that we know of, there's no plan A. There is no plan A. Yeah, it's just we have to be lucky. Yeah, that maybe something that you know, someone, I don't know, by accident, you know, patented or whatever, and it may turn out to be true. Yeah, so it can be. Yeah, but up to now, no one has really seen anything, you know, published or, you know, showing on television or live or whatever to someone that
no
you
credible
really
breakthroughs.
There is nothing out there so far. Yeah, so that's the one thing. So which means there is no, you cannot, you know, say to someone, okay, give me $1 million and I will develop the warp drive, because there's no timeline. So there's no plan A what you can do. So what I'm trying to do, I spend a lot of time to develop infrastructure. Infrastructure meaning, see, we develop the best thrust balances in the world. We develop equipment where you can measure very tiny thrusts, or things that are on high voltage, are operating at high frequencies, are working with lasers and whatever. That's something that doesn't exist. If you look for a thrust balance, these thrust balances, they're either made for much higher thrust values, or if you have a balance and you want to measure the weight of something, then well, you're not able to touch anything. You cannot bring any electricity there, because that will influence the measurement and so on and so forth. So you cannot find something, because there is no measurement equipment to investigate anything in that area. Yeah, because so I'm here to develop that. So I develop measurement equipment that goes into an unknown area where we haven't checked so far. We haven't checked if there's any weight influence under these and these circumstances, because this measurement equipment up to now didn't exist. So I'm trying to build infrastructure to check for such kind of things. And I'm using this infrastructure to test some claims that I think are worthwhile just to investigate. And even if I look at it and I already know from past experiments or whatever, it's probably not going to work, I see this as a great measurement and educational expertise, yeah, challenge to see, you know, what do I need to improve on my equipment to make sure I get this measurement right. So I learned a lot, yeah, how to take care of thermal drifts, of electric feed-through connections, of what I have to make sure in my vacuum chamber, and so on and so forth. So we get a tremendous experience of how to do this right. Yeah, which is our asset. So yeah, I don't mind if I get another zero result. Unfortunately, I so much hope that one of these concepts or whatever that I'm testing will turn out to you know, to be the holy grail. Yeah, that would be fantastic. Yeah, well, if I get a zero result, at least I got the more experience in how to improve my measurement equipment, and I can only get better and better. And if by chance I stumble upon something then of interest, then that's great. So yeah.
Well, that, I mean, I think that's a great approach, right? And for one, building out the infrastructure in order to test a lot of these claims. Because if anyone, actually starts to actually look into propulsion, there's a lot of information out there, a lot of claims, a lot of patents. But I think the ability to actually verify these claims, I think that's extremely important, especially in the scientific community. So I think that's a great idea. As far as like your research goes, have you had any anomalous results or any interesting results that you could speak of or that you'd care to talk about?
I publish everything,
Mm-hmm.
and I'm not announcing anything on media that I have not carefully examined and published, because if I would say, hey, I think that's anomalous or interesting or whatever, then
Mm-hmm.
maybe
Fair enough.
lots of people are streaming this, and then they say, hey, Professor Tajmar said, no, 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 no.
Yeah, yeah,
So
understandable.
I carefully choose my words, I hope,
Mm-hmm.
that
Mm-hmm.
that people can somehow trust me. If I say
Mm-hmm. So okay,
there's
so
nothing
where do you
there.
think what do you think is an interesting area of propulsion research now, given our current state of technology? You mentioned nuclear propulsion. You mentioned laser propulsion, with having a fixed laser on the Earth, propelling a very small payload. Are there any other promising areas that you think are going to be interesting in the near future?
Sure. Well, from the normal propulsion concept, so for example, solar sails for sure will be a big push. That's also propellerless propulsion. Everything that is propellerless is great.
Mm-hmm.
So you work on new solar sail materials, extremely lightweight, and this is propulsion for free. There's another free propulsion option, by the way, which is huge. This is called gravity assist. It also deals with gravity. So this is what's being used by interstellar probes. So you go out there, and because these big planets, they move, around the sun. So when you go into this gravitational sphere of influence from, let's say, Jupiter, and Jupiter is dragging you all along with a spacecraft, you get a huge velocity increase by that. So there's another great, propellerless propulsion option that you can use maybe even several times to spin up. But yeah, solar sails for sure will become very interesting. Nuclear propulsion, yeah, near Earth propulsion. Yeah, also dealing with magnetic fields from the magnetic field of the Earth. So tethers. So when you have currents flowing through cables that interact with the Earth's magnetic field, that's also a very interesting propulsion option. You can use this to deorbit satellites, in a propellerless way, which is of yeah, great influence. So we are, for example, in the framework of a European project with partners, we're developing a deorbit kit, for example, based on this type of propulsion system. So there are lots of interesting propulsion concepts out there ready to be explored.
Professor Tajmar, thank you so much. So one last question before we go. So what is your vision of the future?
My vision of the future. You mean in terms of space travel?
Yeah,
or,
in terms of space travel, given the current state of research, what is ideally what would the future look like to you?
Well, that answer is simple. Jules Verne, one of the most influential science fiction writers of all times, he said that everything that you can imagine must be possible because we are part of nature. So how is it possible that we can think something unnatural? So if I see something like Star Trek or science fiction movies or books, I love to read science fiction novels. Yeah, all of this for sure will be possible. that's my thinking. No one knows how the world looks in 1 year from now, right? No one knows.
Right.
So I can just believe whatever I like to believe, okay? And I like to believe that we will eventually solve this warp drive problem. We will go, around, we will discover other worlds, another Earth. We will talk to other civilizations, pretty much like Star Trek. So this is of course a vision that I would really like to see, coming to reality. I think.
Me too.
So, and if it's just wishful thinking, fair enough. But I'm free to to choose whatever I want to believe, right? So
This is true.
I try to think that eventually that's going to be possible. So I'm very optimistic. Yeah.
Professor
Much better
Tajmar,
attitude for me. Yeah.
thank you so much. I share the same vision, by the way. So
Mhm.
once again, thank you for your time. It's a pleasure having you on the Hard Tech podcast. We will post it up in a couple days once we do some editing, and look forward to hearing some more about your research.
Great. Send me a link. Thank
Yep,
you.
we'll do. Thanks. Take care.
Okay. Thank you. Take care. Bye.